Two people are there. Haribada, we'll start paper 21, I guess. We'll start with question number. We'll start with question number 22nd, right? We did discuss until question number 21 during the last class. Haribata, we'll start. Let me share the screen. Hari, this is paper 21. We discussed until question number 21. Now we have question 22, right? This is the question. See, cylindrical piston of mass capital M and cross-sectional area A slides smoothly inside a long cylinder closed at one end, enclosing a certain mass of a gas. The cylinder is kept with its axis horizontal. At the equilibrium position, the pressure inside the cylinder is P, that is given at the equilibrium position. Now, if the piston is disturbed from the equilibrium position, it oscillates simple harmonically. Now, okay, we need to find the period of oscillation. Now that is the question. So how to do this question? Now there is a piston. 21st. There you have a piston cylinder arrangement. The piston is and the cylinder is kept horizontally as shown. And the mass of the piston is capital M. That is given. Mass of the piston is capital M given. And they have mentioned that at the equilibrium position, the pressure inside the tube is P. Pressure inside. Let's say this is the equilibrium position of the piston. The pressure inside the tube is P. And now, and this length of the tube is H. This length of the tube is H at the equilibrium position. The length of the air column is H, and the cross-sectional area of this piston, this area is capital A, that is given. Okay, those are the data. Mass of the piston is capital M. At the equilibrium, the length of the column is H, the cross-sectional area is A, and the pressure inside the tube is P. Now, what happens is, now you are going to displace this piston from the equilibrium position. Let's say you displace this piston a distance simple x. Now what's happened? Now this is the initial position. Okay, this is the initial position. You are going to displace this piston a distance x. Distance x. This distance is x from the equilibrium position. Now the pressure inside the tube will reduce, right? Let's say the new pressure is P dash. The pressure inside the tube will reduce. Why? What is the reason? The temperature remains the same. The mass of the air column remains the same. So according to Boyle's law, when volume increases, the pressure will decrease. Now, initially, right at this point, at the equilibrium position, the pressure from this same, let's say the pressure is F. So pressure force from this side is also F, right? That is why the piston is at the equilibrium position. At the equilibrium position, the resultant force on the piston is 0. So due to the internal pressure, there will be a pressure force in this direction. Due to the atmospheric pressure, there will be a pressure force, right? So we can say at this instant, the atmospheric pressure is also P, right? That is the reason why the piston remains at the equilibrium position. Now what happens is, now we are going to displace. When you displace, the pressure inside will reduce, but the atmospheric pressure will remain the same, right? So the atmospheric pressure will be this same P. But inside pressure has reduced. So now there will be a force difference. Let's say the force from this side is F. The same force will act, right? Let's say this force is F1. So this force is F1. But the internal force will be different. Let's say F2. So there will be a pressure difference. So there will be a force difference. So first I'm going to find this P dash. You can apply Boyle's law. Boyle's law. When you apply Boyle's law, P1 V1 is equals to P1 P2 V2, right? Initial pressure is P. Initial volume is cross-sectional area times H. Final pressure, I took it as P dash. Volume is A times, this length is how much? This length is H plus X. So that is A times H plus X is the total. So you can cancel A. Now you have the pressure inside the tube is PH over H plus X, right? Now you know the pressure inside the tube. Now you can find F2 and you know F1. From that one you can find the force difference or the resultant force acting on the piston. So that is the resultant force will be in this direction, right? Why? What is the reason? Initially, the pressure on both sides of the piston are the same. So the resultant force is 0. Now you increase the volume, so the pressure has reduced. So the internal force, pressure force has reduced, so there will be a resultant force in this direction. There will be a resultant force that is F1 minus F2. So how to find F1? F1 is the pressure force acting on the piston due to the atmospheric pressure. Atmospheric pressure is P, right? Initially at the equilibrium position, the pressure inside the cylinder is P. Equilibrium means the forces are equal, so the atmospheric pressure should also be P. At this point also, the atmospheric pressure is P. Now you can apply F1 minus F2. F1 is atmospheric pressure times area. You can neglect the this section. You can assume the cross-sectional area of the piston is A, minus force on the piston from the internal pressure is P dash A, right? P dash A. This is the resultant pressure, right? So now you can simplify. Now you have F1 minus F2 equals to, you can take A out. So you have P minus P dash. From Boyle's law, P dash is PH over H plus X, right? And there you have A. And you can take the common denominator. When you take the common denominator, you have H plus X, P times H plus X minus PH times the area. Minus PH will be gone. So you have Px times A over H plus X. Or you can write F1 minus F2 is the resultant force. Okay, F1 minus F2 is the resultant force. So you can also say that that is the restoring force, right? That is the restoring force, or the force acting towards the equilibrium position, that is known as the restoring force. Let's say F1 minus F2 is F. So you can write F is equals to PA from this one, right? PA times X divided by H plus X. Now, I'm going to take a small assumptions. In every simple harmonic motion, we take some assumptions, right? In simple pendulum experiments, when a simple pendulum oscillates as a simple harmonic motion, we assume that the angle of the displacement or the amplitude is, or the angular displacement is very small. For that means if the angular displacement is about greater than 10 degrees, we cannot assume that the oscillation is simple harmonic. Let's say this is a simple pendulum, right? This angle is theta. The motion becomes simple harmonic only when this theta is very small, right? If this theta is large, we cannot assume the oscillation as a simple harmonic motion, right? There is assumption. Under that assumption only, we can apply the periodic time equals to 2 pi root L over G. And for a spring mass system, can you remember? For a spring mass system, this is the spring mass, the periodic time is 2 pi root M over K. But there is an underlying assumption. What is that? We assume that the spring is always in the proportionality limit. Can you remember? The spring is in the proportionality limit. If the spring has exceeded proportionality limit, we cannot apply this equation. So there are always assumptions in simple harmonic motions. So now they have given that the piston oscillates simple harmonically. That is given. So that means when you drag this piston and remove, it will oscillate as a simple harmonic motion. So for this to be a simple harmonic motion, F should be directly proportional to X. But there is another X in this place. So we have to take assumption. We can assume if the initial length of the air column is very much greater than this X, if H is very much greater than X, or the displaced length is very small from the equilibrium position, you can say that H plus X is approximately equals to H. If this is negligible, you can neglect that. So H plus X is approximately H. So you have F is equals to how much? P times A times X over h plus x is equals to h. Right? Now you have to put this sign. Why? What is the reason? The restoring force is in this direction. The displacement is in this direction. So you can apply a negative sign to this space. So force in this direction is equals to minus PA over h times x. Right? Do you understand? Now, Buddha, you can apply F equal MA. Now you know the force, you can apply F equals to MA in this direction. Force in this direction is minus PA over H times X. Mass is mass of the piston. Now we are going to apply F equal MA to this piston. Mass of the piston is capital M, that is given. Capital M times the acceleration of the piston. So acceleration of the piston is minus PA over MH times X. But for a simple harmonic motion, you know that the acceleration is equals to minus omega square x, right? A is there, A is here, minus sign is there, x is there. So you can compare these two equations. So you have omega equals to PA over MH, the square root of that one. Now you know what you call the angular velocity. Now we need to find, what is the question? What do we need to know? We need to find the period of oscillation. So how to find the period? Period is 2 pi over omega. T is 2 pi over omega. So T is 2 pi, omega is PA over MH. MH comes to the top, PA goes to bottom. So this is the answer. So periodic time is 2 pi root MH over P, right? That is the answer. See? See, Bata? So the answer is 2 pi, this one, right? MH over PA. That is not rho A, that should be PA. Here, this is not rho, this is P, okay? So answer is first one. First one is the answer. Now for question, we have to take this assumption. Otherwise, we cannot assume that this motion is simple harmonic. For a motion to be simple harmonic, the resultant force should be directly proportional to a displacement from the equilibrium position, and also there is a negative sign. Why? What is the reason? The force and the displacement are always in the opposite direction. If you displace in this direction, the resultant force should be in this direction. So displacement is in this direction, force is in the opposite direction. If you displace to this side, the force will be in the opposite direction, right? The force is always towards the center. So always the force is directly proportional to displacement from the equilibrium position, and there should be a minus sign. If there is a motion like this, it is a simple harmonic motion. To make this to make this equation a simple harmonic motion, we have to neglect this x part. So we can take a reasonable assumption. We can assume that this length is very much greater than this displacement. So x becomes negligible, right? That is how it is done, right? Yeah, Gambutala. This is 20. This is 22nd one, not 21st one. This is 22nd question. Well, now next question. See, 23rd one. Let me erase the board. See the question, 23rd one. See, in question, if QA, QB, QC, and QD are the charges stored in each of the 5 capacitors A, B, C, D, and E shown in the circuit respectively, which of the following statement is true? Hari putala. Now see, there are 3 capacitors A, B, sorry, 5 capacitors A, B, C, D, and E. What can you say? This A, C, and D. Let me draw this one. We need to find the charges stored. Charge stored. 23rd one. A, B, C, and D, and E. And there is a wire, and there is another wire. 18 micro 648 648 80. Okay, Bhutala. These are the 5 capacitors connected in connected like this. Okay. Now we need to find the charge stored in each capacitor. This is capacitor A, this is capacitor B, C, D, and E, right? So when you consider B, C, and D, this terminal is connected to this terminal. Let's say this terminal is terminal X. This terminal is terminal X. So same wire, so same potential, right? So this terminal should also be X, right? If this point is Y, same wire, this point is Y, right? Now consider capacitor B. When you consider the capacitor B, ends are X and Y. When you consider capacitor C, the terminals are X and Y, same thing. When you consider capacitor D, the same 2 terminals are there, X and Y, right? So you can draw the same combination as like this. You can draw the same combination in this way as well. Correct me if I am wrong. This is A. Capacitance is 18 microfarad. This is B, this is C, this is D. Am I correct? Correct, right? Assume this point is point X and this point is point Y. Across point X and Y, there are 3 capacitors. Here also, across point X and Y, there are 3 capacitors. So these 3 capacitors are connected in parallel. That's the case. These 3 capacitors are connected in parallel. And this is E. Now you know the capacitance. This is 6. This is 4 microfarad. This is 8, and the capacitance of E is 80, right? Now this is connected across. This is connected across a 30 volt supply. 30 volt supply. Now, Putala, when you consider the equivalent capacitance, see here 18, here 18, these three capacitors are connected in parallel. When capacitors are connected in parallel, it is similar to the resistors connected series, right? So the equivalent capacitance is here 6, 4, 8. You have to take the addition. So here also the equivalent capacitance is 18 microfarad. Now here 18 microfarad, here 18 microfarad, here also 18 microfarad. So this 30 will divide equally among these three capacitors. So the potential difference across this one is 10 volt. The potential difference across this one is 10 volt. The potential difference across this one is also 10 volt. Now you can find, Puta, the charge stored in each capacitor. The charge stored in a capacitor is Q equals to CV, right? So you can write the charge stored on A. How to write that one? Charge stored on A is 18 times 10. So 180. If you need the unit, that is microcoulomb. The charge stored on E also, charge stored in E, that is also Q equals to CV. Capacitance is 18 times 10, that is 180 microcoulomb. So the charge stored in B, how much? 60. Charge stored on B is 60 microcoulomb. 6 times the potential difference 10. Charge stored on C, that is 4 times 10, 40 microcoulomb. Charge stored on D, that is how much? 80 microcoulomb. So when you arrange these, you have, these are the 5 capacitors. QA is equals to QE, right? These two are equal. Then you have QD. That. Then you have QB. The QC is the minimum. Charge stored on the capacitor C is the minimum. So this is the answer. So what is the answer? See, the answer is QA equals to QE, QD, QBC, DBC. Then you have DBC. So answer is this one, DBC. Answer. Third one is the answer. So when you see this diagram or this circuit, first what you need to take is these three BCD capacitors are connected in parallel. Then you can find the equivalent capacitance. The equivalent capacitance is also 18. So the potential will equally divide among these three combinations. When you know the potential, when you know the capacitance, you can find the charge stored on each capacitor, right? Right. I'm going to erase this section. Okay, next question. Let's move to the question number 24th. See, this is the 24th question. A metallic container is completely filled with a liquid. The coefficient of linear expansion of the metal is alpha metal. Coefficient alpha of metal is given, that is 2 into 10 to the power 6. 2 into 10 to the power minus 6 per degrees of Celsius. And the coefficient of expansion of the liquid, the coefficient of volume expansion, that is gamma of liquid, gamma real, right? Gamma real of liquid is given. Gamma of liquid is how much? 6 into 10 to the power minus 6. 6 into 10 to the power minus 6 per Celsius is the gamma liquid. On heat in the vessel, what are the answers? The liquid will overflow, the liquid level will fall, there will be no any apparent expansion, the level of the liquid will rise or fall depending on the initial volume of the container and the liquid. The level of the liquid will rise or fall depending on the temperature difference. In the question, they have given, see, the metallic container is completely filled, right? Here, that is completely filled. See, completely filled. Hurry. How to do this? Hurry, Utala. Now, there is a metal container. It is completely filled with a particular liquid. And alpha of this metal is given, and the real volume expansivity of the liquid is also given. Can you remember, there is an equation? There is an equation that is gamma real, or the real volume expansivity of the liquid, is equal to gamma apparent volume expansivity of the liquid, plus 3 alpha. Here alpha comes to the vessel. So gamma real is given. How much? Gamma real is 6 into 10 to the power minus 6. We don't know gamma apparent, but we know alpha of the vessel. Vessel is made of a metal, and alpha of metal is known, that is 2 into 10 to the power minus 6. Here 6 into 10 to the power minus 6, 6 into 10 to the power minus 6 will be gone. So you have gamma apparent is equal to 0. Gamma apparent is equal to 0. So what can you say about the apparent expansion? No apparent expansion, right? No apparent expansion. No apparent expansion. Why? What is the reason? When you increase the temperature, the vessel will expand, and the liquid will expand, and the expansion of the vessel and the expansion of the liquid will be the same. So there will be no any visual expansion or apparent expansion. There will be no any amount of liquid that is overflowed, or the volume of the liquid will not fall down. It will remain as the same level. Why? What is the reason? When you increase the temperature, vessel will expand, liquid will expand, so there will be no any apparent expansion. So answer is, what is the answer for the question? The question answer is, there any apparent expansion. There will be no any apparent expansion. Answer is third one is the answer. Third one is the answer. Right? If you need anything. Hurry. Next up. Next question. See, 25th. As shown in the figure, a sound source S, sound source H, which emits a sound of Fs. The frequency of this sound source is Fs. Travel towards a closed tube with a velocity u. Take the sound velocity in air as v, and the fundamental frequency of the tube as f0. Okay. Under what instances the tube resonate? The tube will resonate when the force frequency is equal to one of its natural frequencies, right? Okay. Does the tube resonate from the following? Okay, Buddha. Now, this is the condition. To 25th question. Now there is a 25th. There is a closed tube. Length of the tube is not given. There is a closed tube, and there is a sound source S which is traveling in this direction with a velocity u, and it will emit a sound of frequency. The frequency of the sound is Fs, that is given. Frequency of the sound is Fs, that is given. Now, and the velocity of sound in air is capital V, that is also given. And there is another information, that is the fundamental frequency of the tube is f0. The fundamental frequency of this tube is f0. Question is asking, under what instances does the tube resonate from the following? Haributala. Hari. Let me again share the screen. There are three conditions. See the three condition. Now we need to find under which condition that tube resonates from the following. A is, I write these three. A is U is 0.8V, 0.8V, and frequency is Fs equals to F0. This is the first statement. Second one, or the B, U is 0.8, the velocity of sound in air, and Fs is equals to 2 times the fundamental frequency. And C, U is equals to 0.5 volt, and Fs equals to 1.Fs is equals to 1.5 F0. These are the three instances that we need to evaluate. Okay. Now, here the sound source is traveling with a particular velocity towards the tube. The sound source is not at rest, right? So the emitted frequency is Fs. So from Doppler, can you remember when there is a relative motion between source and the observer, the frequency heard by the observer is different, right? The frequency emitted by the source is Fs, that is correct. But the frequency observed by the observer will be different. Let's say that frequency is F dash. So how to find F dash? F dash is velocity of sound with respect to observer. Tube is the observer, velocity of sound with respect to the observer is V, divided by velocity of sound with respect to the source. Sound is traveling in this direction with a velocity V. Source is also traveling in the same direction with a velocity U. So the relative velocity is V minus U. V minus U is the relative velocity. So F dash equals to velocity of sound with respect to observer divided by velocity of sound with respect to source times the actual frequency. Actual frequency of the emitted sound is Fs. So this F dash is the apparent frequency for this tube or the observer. And Putha, can you remember for a closed tube? For a closed tube, we can write frequency of the nth harmonic is how much? Nv over 4 times L plus C. Or you can also write the frequency of the nth harmonic is equals to what? N times the fundamental frequency. Let's say the fundamental frequency is F naught. So the frequency of the tube is N times F naught. Here N can be 1. For a closed tube, N can be 1. But N cannot be 2. Then you have N3, N can be 5, N can be 7, and so N can be N are odd numbers. It cannot be even for a closed tube. Now, here, this is this is the frequency of the nth harmonic, NF now. Hariputa. And this F dash is the first frequency, right? Now the tube will resonate when this F dash is equals to this Fn, right? When these two becomes equal, the tube will resonate, right? Or when the force frequency is equal to one of its natural frequency, the tube will resonate. Okay, the force frequency is F dash. By this source, this sound source, we are going to oscillate the air column inside the tube. And the oscillating or the force frequency is F dash. If this F dash becomes to one of this NF naught, the tube will resonate, right? So we need to evaluate the conditions. So when F dash is equals to NF naught, the tube will resonate. Tube will resonate. Now, you know this F dash. What is this F dash? F dash Puta, from Doppler, you have VFS over V minus U should be equals to NF naught. This condition should be satisfied, right? Now, let's move to the first statement. Now you have Puta VFS. This is the equation you have for the tube to resonate. This VFS over V minus U should be equal to NF naught. Now you have, I'm going to plug this value to this equation. Let me substitute V. Fs is F naught. According to this one, Fs is F naught. Divide by V minus U is 0.8 V is equals to NF naught. F naught. So you have N is equals to V can be cancelled. That is 1 minus 1 over 1 over 1 minus 0.8. So that is 1 over 0.2. That is 5. So Puta, under this condition, the harmonic number is 5. So 5 is a possible value, right? And N can be 5. So at this instant, the tube will resonate in the fifth mode of vibration. Fifth mode of vibration. So under this condition, the tube will resonate. Now let's move to B part. You have VFS over V minus U equals to NF naught. Now I'm going to plug these things. You have V, here Fs is 2F naught. V minus U is 0.8 V, right? 0.8 V in second one. That is equals to NF naught. You can cancel F naught and V. So you have N is 2 over 0.2. That is 10. So 10 is not a possible answer, right? Here N cannot be 10. We have 1, 3, 5, 7, 9, 11 and so on. So N cannot be 10. So this is not a possible answer. B cannot be. Under these conditions, the tube cannot resonate. Let's move to C. In the C, you have VFS. Fs is 1.5 F naught. Divide by V minus U. U is 0.5 V is equal to NF naught. You can cancel this F naught And this one you have n equals to 1.5 or 0.5. That is 3. So that is a possible answer. 3 is a possible answer, possible harmonic number. So in this case, the tube is resonating with the fifth harmonic, and in this case, the tube is resonating in the third mode of vibration. Okay, third harmonic. B cannot be the answer. So answer is either A and B, not C. So let me share the screen. C only. Answer is fifth one. Fifth one is the answer. Write down these things. Write down these things, Pata. Okay, Pata. Next question. Next question. 26. See, figure 1 shows a part of a circuit of two capacitors C1 and C2. 26. You have two capacitors. There you have a 10-volt cell. This is capacitor C1 and this is capacitor C2, and this point is also grounded. That means the voltage at this point is 0. This is capacitor C1 and this is capacitor C2. Figure 2 shows the variation of electric potential from A to B. See, we need to find the value of C1 or C2. potential versus distance graph is given. There you have potential, there you have the distance. The graph is from there to there 0, suddenly it has increased to 10, 10 volt, from here to here, this one, this is 4 volt, this is 10 volt, this point is A and this point is B. This point is A and this point is. We need to find the ratio in between C1 and C2. How to do that one? Now, Putala, can you see when you are traveling from A to B, the variation of the potential is given. See, Puta, from here to here, the potential is 0. That means from here to here, from here to up to this point, the potential is 0, right? Why? What is the reason? This terminal is grounded. So the potential up to here is 0. From the graph also you can see, suddenly the voltage has increased to 10 volt. That means when you pass this cell, the potential has increased by 10 volts. So the potential at this point is 10 volt. From here to here, the same potential, right? 10 volt is there. From this point to this point, there will be no any potential drop. Why? There is a conducting wire, so the resistance is negligibly small, so there will be no any potential drop. So up to here, that is 10 volt. Now, from here to here, 10 volt. Now there is a sudden potential drop. Why? Now we are traveling through a capacitor. So across the capacitor, there will be a potential difference. From this graph, you can see the potential has dropped to 4 volt. So the potential at this point is 4 volt. And from here to here, the same potential is there. That means there is a conducting wire. From here to here, the potential is same, 4 volt. And when you go from here to here, the potential is 0 volt. See? Now, Puta, you can find the potential difference across each capacitor. The potential difference across this one, here 10 volt, here 4 volt. So the potential difference is 6 volt. Here 4 0 volt. So the potential difference across this one is 4 volt. 4 minus 0 is 4. For a capacitor, can you remember the ratio between the charge, or you can write, hope you can remember, C1 over C2 ratio between the two capacitance is equal to V2 over V1. Can you remember? V2 over V1. C1 to C2 ratio is equal to V2 to V1. So that is equals to C1 over C2 equals to V2 is 4, V1 is 6. 4 over 6. So that is 2 over 3. 2 over 3. The ratio between the capacitance is 2 over 3. Or you can also do it like this. If you can't remember this one, you know when two capacitors are connected in series, the same charge will be stored on both the capacitors. So for this capacitance, that is charge stored is C1 times potential difference is 6. For this capacitor, the charge stored is the same, capacitance is C2, voltage is V. From this one also, C1 over C2 is 2 over 3, right? Same answer will come. If you remember this one, you can directly apply or use this one. So answer is Putala. So this one is 2 over 3. So answer is third one. Third one is answer. Write down. I'll give 1 minute. There is another part. There is another part as well for this question. See, in the above question, the energy stored in the capacitor is C1. Capacitor C1, E1. The energy stored in this one is E1. Okay. Now, the cell in figure 1 is replaced by a 20 volt cell. At this instance, the energy stored in the capacitor C1 is E2. Then, We need to find a relationship in between. Okay. E1 and 2. Now, Puta, first write this one. I'll give few seconds. I did this one. At this instance, the energy stored in this one is E1. That is given. Write down. Haribhuta. Now, in the 27th question, they have mentioned that in this case, the energy stored in the capacitor is E1. So you can find E1, Putala. How to find this E1 energy stored on a capacitor? There are three ways. You can find either half QV, half CV square, or half Q square of C. You can apply energy is equals to half. You know the capacitance? No, you don't know. That is C1. Is it given? No, right? We can take in terms of C1. Hari, Putala. Energy stored in the capacitor is half. Capacitance is C1. Potential difference is 6 volt, right? Half C, volt is 6 square. Can you remember? Energy stored is half CV square for a capacitor. Capacitance is C1. Voltage is 6 volt. So energy stored is E1, that is 18 C1. 36 over 2 is 18 C1. Clear? Now, Buddha, instead of this cell of voltage 10 volt, they are going to replace it with a cell of 20 volt. Now, we can redraw this circuit. There you have the capacitor C1, there you have this is C1 and this is C2. The voltage at this point is 0. So when you replace this with a voltage 20, the potential at this point is 20 volt, right? Now you can find the potential difference across this capacitor. Let's say this is V1. How to find V1, Putala? These two capacitors are connected in series. So the potential across this capacitor is, the total potential difference is 20 times C2. Can you remember? Divide by C1 plus C2. If you need to find the potential difference across this capacitor, that is total voltage times the opposite capacitance divided by the addition. If you need to find the potential difference across this capacitor, that is total times the opposite capacitance, that means C1 over addition. Now, you know this ratio. From that one, you can find V1, right? V1 is equals to how much? 20. Divide numerator and denominator by C2. So you have C1 over C2 plus 1. That is 20. C1 over C2 is no. C1 over C2 is 2 over 3. 2 over 3 plus 1. When you simplify this one, 3 goes to the numerator. There you have 5. So 4 times 3, that is 12 volt. That means the potential difference across this one is 12 volt. And so the potential difference across this one should be 8 volt, right? The total potential difference is 20. The potential difference across this one is 12. So across this one, that is 8 volt. If you need the potential difference across C2. That is not required, I just say. Now they have mentioned the energy stored at this instance is E2. Now, Putha, you can find E2. How to find E2? E2 is half C1 V square. Voltage is 12. 12 square. So you have 12 square is 144 divided by 2. That is 72 C1. This is E2. So you can take a relationship between E1 and E2. You can divide 1 by 2. When you divide 1 by 2, you have E1 over E2. E1 over E2 is equals to 18C1 over 72C1. C1 is gone. So E1 over E2 is equals to 1 over 4. 1 over. So what is the answer? E1, we need to subject E2. So E2 is 4 times E1. E2 is 4 times E1, right? So answer is 4 is the answer. Fourth one is the answer. E1 equals to 4 times E2. When you increase the voltage, obviously the energy stored on the capacitor will increase, right? That cannot be lesser than E1. That should be greater than E1. So E2 is 4 times E1. Answer is fourth one. Right now. Hurry. Next one. Next question. This is the question. 28 one. Read the question. A thermodynamic process is shown in the figure below. PV diagram. Normally, a thermodynamic cycle or a process is represented using a pressure versus volume graph. Cyclic process. There you have a clockwise cycle. It is traveling from A to B, B to C. They have given pressure at A is 3 into 10 to the power 4. Pressure at A is 3 into 10 to the power 4 Pascal. 3 into 10 to the power 4 Pascal. And the pressure at B is 8 into 10 to the power 4 Pascal. Volume at A is 2 into 10 to the power minus 3 cubic meters. And volume at A and B are the same. Volume at D and C are the same. That is 5 into 10 to the power minus 3 cubic meter. In the process AB, 600 joule of heat, and in BC, 200 joule of heat is added to the system. Heat added in the process AB is 600 joules. Heat added means heat input. So that is positive. And heat added delta Q BC, that is 200 joules. 200 joules. That is also given. We need to find the change in internal energy in the process AC. Delta U AC. We need to find delta U AC. Very easy. Now we know delta Q AB. We know delta Q BC. So you can find delta Q AC. You know delta Q AC. You can also find the work done from A to C, right? Work done can be easily found. Then when you know work and heat, you can find the internal energy. First, I'm going to find delta Q AC. Delta Q AC. Work done from A to C. Hurry. Work done from AC. Work done. Delta Q, delta U AC. Hari Butala, let's consider like this. Delta Q ABC, heat added along the path ABC. That is equals to how much? Delta Q AB plus delta Q BC, right? When you are traveling, consider path ABC. Total heat added, or the total change in or the heat input, is equals to delta Q ABC, that is equals to delta Q AB plus delta Q BC. Delta Q AB is given, that is 600. Heat is added, so that is positive. Along the path BC also there is a heat input, so that is also positive. Altogether you have the total heat input of 800 joules, right? Then Puta, along the same path, you can find the work done. Work done along the path A, B, C. Work done along the path A, B, C is this total area, right? Work done, when work done from A to B is 0. Work done from B to C is this total area. So the total work done is this area. So how to find this area? This is 18 to 10 to the power 4 times this distance, that is 5 minus 2 is 3. 3 into 10 to the power minus 3. So that is 24. 8 into 3 is 24. 240 joules. So work done along the path ABC is 240 joules. You can apply first law of thermodynamics. First law, that is delta Q is equals to delta U plus delta W along the path ABC. So ABC, ABC. So delta Q is the net heat input, that is 800. 800. Delta U, you don't know. Work done along the path ABC, delta work is 240. So internal energy ABC equals to 800 minus 240, that is 560 joules. That is positive. So there will be an increment of the internal energy along the path ABC by 560 joules. That is not the question. We need to find the what question? We need to find the change in internal energy in the process AC. In the process AC, not ACP. However, when you consider the path A, B, C, or A, D, C, or AC, the initial point and the final point will be AC, right? So the change in internal energy or the internal energy change only depends on the initial and the final point. You can say delta U ABC should also be equals to delta U ADC. That is also equals to delta U AC. So you can write delta U AC is also the same thing. That is 562. Clear? Same change in internal energy. But Puta, if you are traveling, let's say you are traveling from here to here in this path, the work done will be different. Why? The area will be different, work done will be different. So the heat added will also be different, but the change in internal energy will be the same. So you can say delta Q and delta W are path functions. Path functions. Delta Q and delta W are path function. That means these quantities depends on the path taken, but delta U is a state function. State function. That means that only depends on the initial state and the final state, right? That doesn't depend on the path taken in between the initial and the final. Okay, write down these things. Give me about 5 minutes. I'll count. You can write this. Haribatala, sorry for the delay. Next one, 29. 29th one. Let's go. Light ray is incident at one refracting surface of a glass prism of refractive index 2 kept in vacuum at an angle theta with the normal. The light ray doesn't emerge from the other refracting surface. Doesn't emerge. Okay. Refractive index is 2. That is also okay. Doesn't emerge from the other surface for any value of theta. Which of the following angle is not a possible prism angle? Now, if the incident for any incident angle theta, the light ray doesn't emerge from the other refracting surface. So they are asking what is the anywhere. Which of the following angles is not a possible prism angle? Not a possible prism angle. Okay, Puta. Now, this is 29th question. 29th question. Now, this is the prism. Normally, for a prism, can you remember? When it is traveling, the angle of incidence is theta. That is given. The angle of the prism angle is A. Normally, the ray diagram will look like this, right? For a normal prism. But they have given for any incident angle theta, the ray doesn't emerge through this refracting surface. Okay? So, the ray is not traveling like this. That is what they have given. Haribota. First, I am going to, that means if the ray doesn't emerge or doesn't refract through this surface, that means at this point the angle of incidence is greater than critical angle, right? Greater than or equal to critical angle. That's why the ray doesn't come out of the surface. So first I am going to find the critical angle for the glass. Here you have glass, there you have air. First I am going to find the critical angle for glass air interface. Critical angle. Critical angle is what? When the ray is traveling from, let's say this is glass and this is air. If the angle of incidence is C or the critical angle, the ray will pass along this surface or the angle of refraction is 90 degrees. You can apply Snell's law, that is N glass sine C is equals to N air sine 90. N glass is 2, that is given. Sine C is equals to this term is 1. So sine C is sine C. Sine C is half. So C is how much? 30 degrees. 30 degrees. So the critical angle for what do you call C is 30 degrees. Now Buddha, they have given for any angle of incidence, the ray doesn't emerge. You have, if this is theta and this is R1 and this is R2, you can write A is equals to R1 plus R2, right? Prism angle is the addition. Now, first I am going to assume this. Let's say this is the prism. For any value of theta, the ray doesn't emerge. Let's first consider when theta equals to 90. Let's consider when theta equals to 90. What's going to happen? Here, the theta is 90. or the ray is traveling like this. This angle is 90. When this is 90, it travel like this. But here, this angle is R1, this angle is R2, right, Pudha? R1 and R2. Here, they have clearly mentioned for any angle, the ray doesn't emerge through this surface. So you can say this R2 should be greater than or equal to the critical angle. That's why the ray doesn't emerge. If this R2 is lesser, the ray will refract. If this R2 equals to C, it will go through this surface. When R2 is greater than C, it will totally reflect, right? So Pudha, they have given that the ray doesn't refract through this surface. So you can say when theta here, theta is 90. When theta is equals to 90 degrees, when this theta is equals to 90 degrees, this R2 should be greater than or equal to critical angle. So R2 is how much, Pudha? Greater than or equal to critical angle is how much? Critical angle is 30 degrees. See, we found it. Critical angle is 30 degrees. Hurry. Now, what can you say about this R1? The angle of incidence is 90. What is the angle of refraction? Reversibility of light. When it is traveling with C, when the angle of incidence is C, the angle of refraction is 90. Similarly, when you reverse the ray, it will path, right? So when it is traveling with 90, it will refract with C. So here it is traveling with 90. So this R1 should be equal to 30 degrees, right? At this point, or you can apply Snell law and find R1 should be equals to 30 degrees. Again, Pudha, you know that here A is what? A is the prism angle is R1 plus R2, right? So at the place of R2, you can write A minus R1. Why? A is equals to R1 plus R2. So R2 is A minus R1. Should be greater than or equal to 30 degrees. So A should be greater than or equal to R1 plus 30 degrees. So A should be greater than R1 is also 30 degrees. 30 plus 30. So prism angle should be greater than 60 degrees. Now, Pudha, the other thinking is, now when the angle of incidence is 90, if this condition is satisfied, the ray doesn't emerge. What can you say about the other angles? That means let's consider this angle or theta is lesser than 90. When theta is lesser than 90, what happens, Pudha? When theta is lesser than 90, this R1 will decrease. Right? R1 will decrease. According to the equation, A equals to R1 plus R2. When R1 decrease, this R2 will increase, right? The prism angle is a constant, right? So what happens is, I'll write when when theta decrease, what happens? R1 will also decrease according to Snell's law. From this equation, according to this equation, when R1 decreases, this R2 will increase. This R2 will increase. So, Pudha, when R2 increase, it will be greater than this one, right? So, for all other angles, the angle of incidence at this point will obviously greater than C. So no total internal reflection will take place for other thetas as well, right? Then when this theta is equals to 90, for the ray to not to refract to the surface, this condition should be satisfied. For other angle, if this condition is satisfied, for theta equals to 90, the ray will not refract. Why? If this condition is satisfied, R2 is greater than or equals to C. So the total ray will totally reflect. For the angles means if theta is lesser than 90, when theta is lesser than 90, this R1 will be lesser. When R1 is lesser, R2 will be obviously greater than this one, right? So for other angles as well, the ray will not penetrate through this refracting surface, right? Am I clear? So Buddha, for the ray to not to refract through this surface, for any angle of theta, this condition should be satisfied. According to this one, the prism angle should be greater than 60. The prism angle should be greater than 60 for this condition to satisfy. So the prism angle cannot be lesser than 60 degrees. Let's move to the question. Now, if the light ray doesn't emerge from other refracting surface for any value of theta, which of the following angle is not a possible prism angle? The prism angle should be greater than or equals to 60. So the answer cannot be 45, right? Prism angle cannot be 40. They are asking which of the following angle is not a possible prism angle. So answer is 45. Answer is second. Second one is the answer. One is the answer. Clear? Very important. Write down. If this ray doesn't penetrate through this surface for theta equals to 90, for every other angles also this ray will not penetrate to the other surface. So the condition is we need to find this one when theta equals to 90, right? When theta equals to 90, if this one is greater than critical angle, for every other angle, this one should be greater than, obviously it is greater than the critical angle. Okay, next one, Putala. As shown in the figure 1, two plates A, okay, are placed between the charged parallel plates P and Q. The figure 2 shows the electric potential variation graph from P to Q. Select the correct answer regarding the plates A and B. Now, Buddha, when you consider the potential, this is the potential versus distance graph, right? Distance graph is given. Potential versus distance graph. Now, when you consider this is the potential versus distance graph. Now, can you remember, Puta? Now we need to find A and B. Select the correct answer regarding. Now, when you consider inside A, the potential is this, right? This is inside A. Inside B, the potential is a constant. Can you see? Inside B, the potential is a constant. So, can you remember for a conductor? For a conductor, electric field inside a conductor is zero. Electric field strength inside the conductor is zero. When the electric field inside the conductor is zero, the potential gradient is zero. The potential gradient is zero, so the potential is constant along a conductor. So this B should be a conductive. And when you consider a dielectric medium, there is a electric field strength, so there will be a potential gradient. So this is dielectric. Let me explain that part. When there is a conductor inside, let me draw conductor placed inside a capacitor. When a conductor is placed inside a capacitor, let's say these are the two capacitor plates. This is positive and this is negative. Let's say you have a conducting plate. Assume it as a metal plate. When you place a metal plate, this side becomes negatively induced. So this side becomes positively induced. So there will be an electric field from here to here. There will be an electric field from here to here. But inside a conductor, electric field strength is zero. So, Buddha, if you draw the electric field strength versus distance graph, that is like this. When you draw electric field strength versus distance, from here to here, constant electric field strength. From here to here, zero. Zero electric field strength. Electric field strength is zero. From here to here also same. Can you remember there is an equation like this? E equals to minus dV by dx. dV by dx is the potential gradient. That means the gradient of the potential versus distance graph is the potential gradient. That is equals to electric field strength. Now for this one, if you draw V versus X graph, that is like this. From here to here, there is a constant electric field strength. So there is a constant gradient, but the gradient is negative, constant negative gradient. From here to here, electric field strength is zero. So the gradient becomes zero. So gradient of this graph is zero. See, slope is zero. So that is a parallel line to the x-axis. From here to here, there is a gradient. So if you draw the potential versus distance graph, when a conducting plate is placed, inside the conductor, the potential or the voltage is constant throughout the conductor. But if you place a dielectric medium is like a insulating medium, like a paper or glass or wax, like an insulating medium. Now I am going to place a dielectric medium. Inside a conductor. Inside a capacitor. Let's say this is positive. This plate is positive. This plate is negative. You place a dielectric medium. From here to here, there will be electric field strength. Same electric field will be there from here to here. From here to here, there is electric field strength, but this is lesser than E1. Why? What is the reason? There you have vacuum. There you have a dielectric medium. Electric field strength is sigma over E1 is sigma over epsilon naught. E2 is sigma over K epsilon. Can you remember? Here K is the dielectric constant. Now, Buddha, when you draw the electric field strength versus distance graph, that is from here to here constant electric field strength, from here to here constant electric field strength. But inside the dielectric medium, there is there is an electric field strength, but it is lesser than the electric field strength outside. If you draw the voltage versus X graph, that is from here to here, there is a constant gradient. From here to here, constant gradient, but the gradient is lesser, right? The value is lesser, so the gradient is less. From here to here, the same gradient. These two are parallel, right? That is how it looks. Now let's move to the question. See, Puta. Now this is the question. See, when you consider this A, there is a potential drop. So it is a dielectric medium. When you consider B, see the voltage same. The voltage same means that is a conductor. So the answer is dielectric conductive. Answer is first one. First one is the answer. For the 30th one, first one is the answer. Write down Puta. ඕනේ තියන ලියලා. හරිද පුතාලා? Inside a capacitor, the electric field strength is sigma over epsilon naught. Sigma is the surface charge density. Epsilon naught is the permittivity in free space. There K is the dielectric constant. That is the ratio between permittivity of the medium to permittivity in free space. Okay, let's move to the next question. Okay, next question, 31st one. See. This is the question. In the circuit shown, R is a variable resistor and RC has a fixed value. When R is at its maximum value, the transistor is biased to active region. When R gradually decreased, what's going to happen? Now this is a transistor biased. A transistor can be biased by using two ways. One is the base resistor method, other one is the potential divider method. This is the base resistor method. The transistor is biased by using the base resistor method. This is the base resistor method. V out. This is PNP transistor. This point is grounded. There you have the output voltage. V out plus VCC. Base current is IB. IB. This is the variable resistor R. And there you have IC and RC. IC and RC. So what are the answers? The base now you are going to decrease R gradually. Now they have given when R is at its maximum value, the transistor is in the active region. That is given. See, when R is gradually decreased, now you are going to decrease R, the base current, collector current, and the output voltage. Now see, this is our circuit. Now, collector current is IC and the resistor is RC. Supply voltage is VCC, output voltage V out, base current is IB, and there is a variable resistor. Now, this variable resistor is at its maximum value. When the variable resistance is maximum, they have given that this is in the active region. Now, we are going to decrease this up to 0. You are going to decrease this. Now, Bhuta, first, what are the things that you can write? This is base. This is emitter and this is collector. Now I'm going to consider this branch. When you consider this branch, the potential difference is how much? Here the potential is VCC, here the potential is V0. So the potential difference is VCC minus 0. So VCC minus 0 is how much, Putala? VCC minus 0 is how much? IBR. IB is the base current. IB times R plus the base emitter voltage, VBE. So you can write VCC minus VBE is equal to IBR. VCC minus VBE is a constant. So when you are going to decrease R, when you decrease R, this IB will increase, right? So when you decrease R, the base current will increase, right? Then also you can write when base current decrease, since this is in the active region, you can write beta is equals to IC over IB. Clear? When IB decrease, what happens to this IC? This IC will decrease, right? Why? What is the reason? IB equals to, see, IB times beta is equals to IC. When you decrease this one will also decrease, right? Or can you remember the transfer characteristic? Transfer characteristic is IB versus IC. That is like this. When you decrease IB from here, this is active. When you decrease IB, this IC will also decrease, right? Then again, what can you say about the output voltage? V out. How to find the output voltage? Output voltage is VCE is the output voltage, right? Now, you can, by considering these two, you can write VCC minus V out. VCC minus V out, voltage at this point minus voltage at this point, is equal to ICRC. So you can write V out, output voltage, is VCC minus ICR. VCC is a constant. Now when you decrease R, IB will increase. When you decrease R, IB will increase. Okay. When IB increase, IC will increase. Sorry. Here you are going to decrease R. When you decrease R, IB will increase. When IB increase, IC will increase. From here, when IB increase, IC will increase, right? Up to here, up to the saturation current, IC will increase. When IC increase, what happens to the output voltage? See, when this one increase, the negative term part will increase, so output voltage will decrease. So ultimately what's going to happen? You are going to decrease R. When you decrease R from this one, IB will increase. When IB increase, what happens to IC? IC will also increase. When IC increase from this term, output voltage will decrease. V out will decrease. That's what's going to happen. Now, see. Now, when R gradually decrease, the base current will increase. First one is correct. Collector current will decrease. Wrong. Collector current will also increase. That is wrong. The output voltage will decrease. That is correct. So, is correct. C is correct. So, answer is fifth one. Only A and C are true. Only A. Write down. Write down, Putta. තේරුණානේ? මේ පැත්තට ලිව්වා VCC minus 0 is equals to IBR plus VB. From that one, VCC minus VB equals to IBR. When you decrease R, IB will increase. This term is a constant. According to this one, when IB increase, IC will increase. From transfer characteristic also, you can say when you increase IB, this IC will increase. When IC increase, when current increase, V out will decrease, obviously. I'm going to erase this. Okay, next question. Next question. 30 seconds. See, a steel wire of 0.8 millimeter and length 1 meter is clamped firmly at two which are 1 meter apart and in the same horizontal plane. The body is sunk from the midpoint of the wire such that the middle point sags 1 centimeter lower from the original position. What is the total extension of the wire at this instance? That is the question. Now, this is the question. 30-second question. 30 seconds. There is a wire of length 1 meter. This wire is length 1 meter, and it is clamped firmly between two horizontal points A and B. Now we are going to attach a weight to the center point. So now what's going to happen? This wire will bend like this, or the wire will extend and bend to form a shape, Y shape, like this. A weight has been attached. This is the weight. Let's say the weight is not given. The weight is, let's say, mg. Now, initially, this length is 100 centimeters. So this is the center point. The weight has been attached from the center point. So this is 50 centimeters. From here to here, the length is 50. So that is also 50 centimeters. 50. They have given that the wire sags down by 1 centimeter. This is 1 centimeter. That is given. This is 1 centimeter. Okay. Now, Buddha, in the first question, what is the total extension of the wire at this instant? The total extension is, the initial length is 100 centimeter. Now, the new length is this one, right? The wire has been extended. Now, we need to find the new length. When you know new length, when you know the initial length, you can find the extension. For that one, you can find this distance. Let's say from here to here, the distance is x. By considering this triangle, you can apply what you call Pythagoras theorem. So 50 square plus 1 square is equals to x square, right? From Pythagoras theorem. So let's say this point is point C. So you can apply Pythagoras theorem. AC square is equals to 50 square plus 1 square. So AC is 50 square plus 1 square, the square root. So the answer is what? What is the answer? You can simplify this one. So that is square root of 50 square plus 1. 50 square plus 1. That is 50.009 something. That is approximately 50.01 centimeters, right? That is the AC length. Now you can find the final length. What is the final length, Buddha? 2 times of this one, right? That is 50.01 times 2. That is 100.02 centimeter. This is the final. So you can find the total extension, that is delta L. How to find delta L? Final length is this much. Initial length is 100 centimeter. So the extension is 0.02 centimeter. So the answer is 0.02 centimeters. Answer is 0.02 centimeter. And second one is the answer. Calculate the mass of the hung body given of the material of the wire. They have given Young's modulus. That is 2 into 10 to the power 11, 2 into 10 to the power 12 Pascal. The mass of the attached weight, mass of the hung body, mass. We need to find the mass. So how to find the mass? Now, Putala, you know that by this mass, the total extension of the wire is known, right? Total extension of the wire is known. Now, let's say the tension on this section is T, and this angle, let's say theta. For the horizontal equilibrium, this angle is also theta. So this tension should also be T, right? Why? T sine theta, T sine theta has to be cancelled. So the tension at this wire is also T. By considering the vertical equilibrium of the point C, you can write T cos theta, that is 2T cos theta should be equal to mg. 2T cos theta should be equal to mg, right? 2T cos theta should be equal to mg. තේරුණා නේද පුතා? if you consider the tension on this section is T, the tension on this section should also be T. Now you can write, by considering the vertical equilibrium of point C, you can write 2T cos theta should be equal to mg. 2, so you have T equals to, okay, 2T cos theta equals to mg. Now Buddha, how to find this T? Is there a method to find this T? Yes, right? How to find this tension? The tension on this wire? There is a method. Can you remember? T in the Young's or the elasticity, you have been told that F equals to AY over initial length times the extension, right? F is this tension is equals to area Young's modulus initial times delta, right? So you can write that at the place of T. So T is AY over initial length times extension times cos theta should be equal to mg. Now the only unknown term is mass. You can find that one. So now I'm going to substitute the values. Area of this y is, they have given that the diameter of the y is given. In the initial part, they have given that the diameter of the y is 0.8 millimeter. So the area is pi times radius is 0.4, that is millimeter. You have to convert it into meters, that is 4.4 into 10 to the power minus 3. Square of that one, pi r square. Young's modulus is given, that is 2 into 10 to the power 12. Extension, how much is the extension? Extension of this section, the total extension is 0.02 centimeters. So the extension of a single y is 0.01, right? Is it clear? Extension of a single y is 0.01 centimeter. You have to convert it into meters. 0.01 into 10 to the power minus 2 divide by the initial length. Initial length of this section is how much? This section, that is 50 centimeters, right? That is 50 centimeters. Initial length is 50 centimeters. You need to convert it into meters. 15 to 10 to the power minus 2 has to be multiplied by cos theta. Cos theta is how much? Cos theta is Putala. Cos theta is, when you consider this angle, cos theta is adjacent over hypotenuse. Adjacent is 1, hypotenuse 1 over 50.01. That is cos theta. 1 over 50.01 is equals to m times 10. So you can divide by 10. When you simplify this equation, you can get the mass. It is up to you to simplify. I'll use the cal. You can simplify. So 2 times pi times 0.4 is the radius, 10 to the power minus 3 square into 2 into 10 to the power 12 is the Young's modulus, and the extension of a single section is 0.01 into 10 to the power minus 2, need to convert into centi, divide by, there you have 500 to 15 to 10 to the power minus 2 into 50.01. 50.01. When you simplify this one, you have 0.8 kilograms. 0.80 kilograms. 0.8 kilograms. That is the answer. So, Buddha, let's move. Let's share the screen. So the answer is here 0.8 kilograms is the answer. You need to simplify. So answer is first one. First one is the answer, right? For this one, second one, for 33rd one, this is 33. The answer is first one. Okay. Now next up. Alright, 34th. The magnitude of gravitational field at distance r1, r2 from center of a uniform sphere of radius capital and mass capital M are F1 and F2 respectively. The magnitude of gravitational field. Gravitational field means gravitational field acceleration. Consider the following statements. 34th. Now there is a sphere. The radius of the sphere is capital R. Let's consider 2 points. Just take this is point A, which is outside the sphere, and let's consider a point inside the sphere as B. Can you remember the gravitational field strength outside, or gravitational field strength at A can be written as Gm over M is the mass of this one. Gm over distance from here to here, if it is R, Gm over R square. So you can write gravitational field strength outside is inversely proportional to R square of the distance. And when you consider a point inside, that is point B, the gravitational field, if you assume this as a homogeneous sphere, the gravitational field strength can be written as 4 over 3 pi rho g. Pi rho g times r. R is the distance. Here rho is the density of this medium, or the density of the spherical object. G is the gravitational acceleration. So Puta, when you consider a point inside, the gravitational field strength is directly proportional to the radius. Clear? This is when r greater than to r. This is when r greater than to r. This is when r lesser than r. Okay? If you consider a point inside the sphere, the gravitational acceleration is directly proportional to the radius. If you consider a point outside the sphere, the gravitational field strength is inversely proportional to r square. If you want to draw a graph, it is like this, Putala. If you draw G versus, don't have enough space. Consider this is a planet. Gravitational acceleration, this is G versus R graph. That is like this. This is capital R, radius of the planet. From there to there, from inside the tube, inside the sphere, the gravitational field strength vary linearly. And outside the sphere, it is like this. G inversely proportional to R square. Here, G directly proportional to R. Okay. Now, now this is the question. The magnitude of the gravitational field at distances R1 and R2. Now, if R1 is less than R2 is lesser than R, that means the point inside the sphere. So the force is direct, or the gravitational acceleration is directly proportional to the radius, right? So F directly proportional to R1, F2 directly proportional to R2. When you divide, you will get this answer. So A statement is correct. And for B statement, if you consider point outside, that means R1 greater than capital R, R2 greater than capital R, you have force or the gravitational acceleration proportional to R square. So F1 inversely proportional to R1 square, F2 inversely proportional to R2 square. So when you divide these two, right? Not this one, or not this one, not this one. You cannot get this one. If the radius is lesser, you will not get this one. So the answer is A is correct and B is correct. So answer A, B correct. Second one is the answer. Second one is the answer. When you consider a point inside, G is directly proportional to R. When you consider a point outside, G is inversely proportional to R square. Write down if you need anything. Hurry, next one. 35. This is the question, 35th one. See, a glass slab. A glass slab. See, there you have a glass slab. This is the glass slab. Here you have a glass of refractive index 1.5 and thickness 3 centimeter is placed with its faces perpendicular to the principal axis of the concave mirror. There you have a concave mirror. This glass block is, see, this angle is perpendicular to the principal axis of the curvature 10 centimeter. That means this is the concave mirror, right? Radius of curvature means distance from C to P. Pole to this one, the radius is given 10 centimeter. Radius of curvature is that. At what at what distance must an object be placed Placed that the mirror so that the image coincides with the object. Image coincides with the object. Note the glass slab is placed in between the object and the mirror. Placed in between the object and the mirror. So object is somewhere there, right? Object is somewhere there. When you place the object here, the image will be formed exactly on top of it. That is what they have mentioned. At what distance must the object be placed from the mirror so that the image coincide with the object? Okay, but how to do this? Very important question. Very smart or nice question. How to do this? To do this question, you need to know these things. Can you remember, Puta? This is 35th one. Can you remember? Yes, 35th one. If you place, let's say this is a glass block. This is a glass block. If you place an object underneath it, and if you draw the ray diagram, can you remember ray diagram? Yeah. This will be traveling away from the normal. Image will be formed somewhere there. Image will be formed somewhere there. Can you remember? There is an apparent shift. If you consider there is a fish inside a water tank, when you observe from top, the fish is appeared to be at a higher location than its original location, right? That means there is an apparent shift. Image will be somewhere there. Object is here, but there will be an apparent shift. Image will be somewhere there. And this apparent shift, let's say this apparent shift is x, and if t is the thickness of this glass block, and let's say the refractive index of this glass is n, you can write this x, right? Apparent shift is equals to what? T 1 minus 1 over n. T is this height, n is the refractive index of the medium. Can you remember? And Puta, in the theory class, I told you the apparent shift doesn't depend on the location of the object. That means if you place the object somewhere even below, the apparent shift will be the same. That means, Putala, let's say this is our block. The thickness is T. If you place the object here, let's say initially it was here. If you draw the ray diagram, it is like this. The ray will travel here towards the normal, and it will travel away from the normal. Away from the normal. Image will be somewhere there. This is the object, this is the image. But Puta, this distance is also x, right? If you place the object here, the image will be formed there. This height is the apparent shift. Apparent shift is this. But if you place the object even or a different place, somewhere like this, the apparent shift will remain the same. That means x is equals to t 1 minus 1 over. Apparent shift doesn't depend on the location of the object. I meant the shift. The apparent depth will change, obviously. For here, the apparent depth is distance from here to here. Here, the apparent depth will be distance from here to here. This distance and this distance are different. That is obvious. But the shift, the amount that the image is shifted or the object is shifted will remain the same. Okay. Now let's move to the question. Now there is a concave mirror. This is the concave mirror. Now I'll do another theory part. For a concave mirror, Puta, can you remember? Let's say this is a concave mirror. concave mirror. This is the principal axis. Can you remember the light? See, the light rays, if a light ray incident traveling through the center, it will retrace the same path. It will refract or reflect along the same path. It will reflect along the same path. Again, let's say a light ray is traveling parallel to the principal axis. If this is parallel to the principal axis, it will reflect to the focal point. It will reflect to the focal point. Or when the light ray is traveling through the focal point, it will reflect reversibility of light. If it is traveling this way, when you reverse, it will retrace the same path. If the light ray is traveling center, it will reflect through the center as well. Okay. Now, Buddha, in the question, they have given the object here. This is the, let's say this is our principal axis. Now, I'm doing the question. I have, this is the concave mirror. This is the concave mirror. A glass block is placed like this. A glass block. And the thickness of the glass block is also given. The thickness is how much? 3 centimeter, right? The thickness of the glass block is 3 centimeter. Yes, that is given. And the refractive index, this is given. And the refractive index of this one is also given. That is 1.5. That is given. Now they have mentioned that the radius of curvature, C is somewhere there. And this point is P. Okay. This is C. They have given that PC distance is 10 centimeter. Radius of curvature is 10 centimeter. That is given. At what distance must an object be placed from the mirror so that the image coincides with the object? Now, the image coincides with the object. Now, Huta, for the image to coincide with the object, can you remember for a concave mirror, if you place the object at C, the image will coincide with the object, right? Now, what needs to happen is here. Let's say you place the object somewhere there. The image needs to coincide with the object. So that means, let's say a light ray is coming. I'll draw a single light ray. A light ray coming from the object, let's say, travel to the glass block and refract, and the refracted ray should travel to the center, right? The refracted ray should travel to the center. Why? The refracted ray should travel along this path. Then only the light ray can retrace or travel along the same path in the reverse direction. If the light ray refracting through this glass block seems like to travel from the center, then only the light ray will travel or retrace along the same path. Then only the object will coincide with the image, right? Or the image will coincide with the object. So the refracted ray from this glass block should travel as appearing to travel from the center. If a light ray is traveling from center, then only it will return along the same path. For the image to coincide with the object, the reflected pattern or the reflected ray should travel along the same path. The refracted ray from this glass block should travel like this. Then, where do we need to keep the object? Can someone tell me where do we need to keep the object? The object. Now consider this one. Now consider this one. See, when you rotate this one by 90 degrees, now the ray needs to travel from C. Right? Here, the ray needs to travel from point C. So you need to keep the object somewhere beyond C, right? Somewhere there. The object is placed at this point. Let's say object is O. Now, when you draw the ray diagram, how to draw the ray diagram? The light ray traveling from this path will incident and will travel towards normal, and travel away from normal, right? Same pattern. Light ray travel towards normal, away from normal. However, this ray should appear to travel from the center here. The refracted ray is appearing to travel from this center. Then only the same ray will reverse and retrace the same path. Clear? This distance can be found. This distance is from here to here, this distance. So CO distance can be found in a similar way. CO distance is when you place the object, the image will be formed there. So CO distance can be found, that is T1 minus 1 over. Here T is 3 centimeter, that is given. 1 minus 1 over n is also given, that is 3 over 2. So 2 goes to top. So when you subject this one, you have 1 centimeter. So CO distance is 1 centimeter. So from P to O, what is the distance? We need to find the location of the object. Location of the object is PO distance, that is PC plus CO. Now you know CO 1 centimeter. PC means how much? PC means 10 centimeter. So 10 centimeter plus 1 centimeter, that is 11 centimeter, right? Now, when you place the object at this point, the image will exactly coincide with that point. මෙහෙම light ray එක high return වෙලා එහෙමම එනවා. හරිනේ? same path එක retrace කරනවා. Same path එක retrace කරන්න නම් මෙතනින් refract වෙන ray එක should appear to come from the center of curvature. Then only the light ray will retrace in the same path. So the object distance, PO distance, should be 11 centimeter. 11 centimeter. See bata in the question. See, at what distance must an object be placed? An object be placed from the mirror. The image coincide with the object. Right? So answer is 11 centimeter. Fourth one. Right down. Fourth one is the answer. Fourth one is the answer. Very important question. In concave mirrors, when you place the object at the center of curvature, the image will be formed on the center of curvature, right? Now, what we are going to do is, we are going to place an object or place a glass block and place, if the glass block was not there, for the image to coincide with the object needs to be placed at the center, right? If the glass block was not there, when you place the object at C, the image will be formed at C, right? Now there is a glass block. So if you place the object here, the image will appear somewhere there. So the image cannot coincide with the object. But if you place the object there, this glass block will create
an image of that one at this place. Okay, this image will be the object to this what do you call concave mirror. So this mirror will try to create the image on this place, but due to this glass block it will shift to this place, right? So the object and the image will coincide. For the image and the object to coincide, the light ray should travel exactly along the traveling path. Light ray should exactly retrace the same path in order to create the image on top of the object. Clear? So the light, the refracted ray through this glass block should appear to travel from this center of curvature. If this travels to C, it will refract along the same path, or it will reflect along the same path. So it can travel along the same path. So the incident ray and the reflected ray will travel along the same path. So the object and the image will coincide again, right? So answer is 11 centimeters. We can do the next 36 question, that is also from this from the same question. Distance from pole is this P, to the surface AB is X. This distance is X. The most suitable value for X could be. Okay. Now Puta, for this to happen, we can keep, when you place the object at this point, we need to create the image at this point, right? I told you, this apparent shift doesn't depend on the location of the glass block. If you place the glass block here or here or here, the apparent shift will be the same. That means, Puta, if you place the glass block here, that doesn't affect this distance, right? For this shift, the location of the glass block doesn't affect. So you can place the glass block here or here or here, or the last location is, I'll draw it here. This is the location of the object, and this is the center of curvature. This distance is 10 centimeter. This is 1 centimeter. We found it. We can place the glass block here. No issue. When you place the glass block here, the light ray will appear to travel from C. Clear? Appear to travel from C. Okay. If you place the glass block here, same thing. If you place the glass block here, same thing. But you cannot place the glass block here. You cannot place there. So you can move this glass block. The last location is this location, right? This is the last location for the glass block. So the last location for X is this distance from here to here. This distance is the last location for X. So X should be greater than or equals to 0 and lesser than this length. What is this length? From here to here, that is 11 centimeter. The thickness of the glass block is 3 centimeter. So from here to here, the length is 11 minus 3, that is 8 centimeter. So you can place the glass block anywhere in between 0 and 8 centimeter. 0 and 8 centimeter. Okay. If you place the glass block here or here or here or here, up to this point, the image and the object will coincide. Clear? That is the answer. So now, what is the answer for the 21st one? In the above question, the distance from pole to the surface AB is X. Okay. The most suitable value for X could be, X can exist in between 0 and 8. X should be in between 0 and 8. Location for X when x cannot be 5, greater than 8, x is less than so answer is 5th, right? As well, x can be 8, so the answer is x should answer is anywhere in between 0 and 8. So for any value of x lesser than 8 centimeter, the condition is satisfied. So the answer is answer for the 36th one. Okay, x should be lesser than x should be lesser than that term. මේ box මේ glass block එක පුතාලා මේ glass block එක මේ මෙතන තිබ්බත් apparent shift එක මෙතනමයි. මේක තව ටික කියන්නේ. හරිනේ? මෙයා උස්සලා තිබ්බත් මේ shift එක එකම. මෙයා තව ටිකක් ඉස්සුවත් ඔය shift එක මේ shift එක මොකට හම්බ වෙනවා. හරිනේ? අපිට වෙන්න ඕනේ ඒකනේ පුතා. වෙන්න ඕනේ එක. මෙන්න මේ ray එක මේ c කින් යනවා වගේ පෙන්වන්න ඕනේ. හරිනේ? එතකොට කොහෙ තිබ්බත් මේ shift එක හොමම හම්බ වෙනවා. හරිනේ? මෙතන නිකන් අර ඔබ්ජෙක්ට් එක තිබ්බා මෙතන නිකන් ඉමේජ් එක හැදුනා වගේ shift එක එකමයි shift එක එකම වුණා ලයිව් ray එක එතනින් එනවා වගේ තමයි පේන්නේ හැමතිස්සම ක්ලියර්ද හරි පුතාලා අදට ඇති හෙටත් කරමු we'll do tomorrow as well okay it's enough for the day and I'll end the live session so God bless you we'll meet tomorrow as well.